existing in the original function. So even though it's simplified, so she said the f of x function, when you factor the numerator, the x squared minus 9 is the difference of two squares. So the x minus 3 cancels, and then that creates the f of x, which is of being x plus 3. However, the original function still has this in the denominator, and because it's still there, it doesn't affect your doing. So even though it cancels, if I would be given this as an original function, if they said like, hey, plug in 3, you couldn't plug it into the original function. So it's always the original function that still is going to affect the entire answer, even if it's simplified. So, because the original function is a fraction, it does have something in the denominator. If you set that equal to 0, that's where your asymptote would be your undefined value. So your undefined value would be at x equals 3, x cannot equal 3. It's still making the original function undefined, even if it does simplify. It still makes the original function. And then the g of x would be right. So by looking at those two domains, no, they're not equal, they're not the same. So yes, the function simplifies, but it's the original function that affects the entire problem or the entire domain. The next question says, does f of x have a vertical asymptote? Explain, Kirsten. Right, so the denominator where there would have been a vertical asymptote, because it's canceling out, it is changing your function. And it's changing it to be x plus 3, which is no longer rational. If it's not rational, it doesn't have an asymptote. A line does not have an asymptote. An asymptote makes the y go to negative infinity, or the positive infinity, or the y go to negative infinity. So there's not a vertical asymptote when a portion of the graph cancels. It's canceling and actually taking that piece of the graph out. So this piece of the graph has kind of vanished from the problem, and it creates a hole in the graph. So there is a vertical asymptote, but there is a hole in the graph. And that hole is at x equals 3. So usually we would say there's an asymptote at x equals 3. But because this is now a linear function, lines don't have asymptotes, but it would have a hole. So whatever piece canceled from the problem is where your hole exists. And that's for any kind of rational function. If you have a portion that cancels, that piece gives you the hole in the graph. So now there you a little hole at x equals 3. So then the last part says, explain why the graphs appear to be identical and then describe their differences. An easy way to explain in math is just to draw the two graphs. So if I'm explaining why they appear to be identical, well, they're appearing to be identical because f of x is now x plus 3, and g of x is x plus 3. So they're both x plus 3. So if I'm just looking at the fact that they're x plus 3, they do appear like they should be the same exact graph. If you would graph this so that we can kind of explain what the difference would be between the two, or show with the graph. If you put this on your calculator, doing them individually, the first one would be undefined. So if you went to the table of values at x equals 3, it would say undefined. If you graph this one, you're not going to have any undefined values. So it's graphing the original function of the calculator. So my g of x function, graphing this would start at the y-intercept of 3, and it's just going up 1 over 1 for the slope, or down 1. So this would be the graph from your calculator. If you place it in your calculator, that's what it would be. For f of x, if you plug it in your calculator, you got to plug the original function in. The graph that you're going to get will look exactly like x plus 3, except there's a hole in the graph. This has the hole at x equals 3. So when I graph it, I want to make sure that I'm showing where the hole is. So if there's a hole at x equals 3, can get that whole point. Why 6? Yeah, so if x is 3, my whole is going to be at 6, because if I plug 3 in, 3 plus 3 is 6. So at the value of 3, 6, it's a point in this graph, in the g of x graph. But in the f of x graph, it's actually a whole, and I would literally draw it as a whole. So right there, 2, 3, 4, 5, 6. That's my whole, the piece that was eliminated from the problem by canceling the numerator and the denominator. But the rest of the graph would be exactly the same as g of x. So they look the same. In the calculator, they're going to look the same because the calculator doesn't draw the whole. But the one on the left is missing just that 1.36, and it's because that point canceled from the denominator. So not all functions have asymptotes if they really aren't rational functions. It appears to be a rational function, that's the way it's set up. But because it's simplified, it actually isn't a rational function. If you take the x value of 3 and just plug it into the equation. Other questions? So how about from either of the homework assignments, whether it was the book or the worksheet? What questions did you have? You're doing intervals of increasing, so like on which intervals is the function increasing? You're using the x values to find the intervals where it's increasing. So since I have number 3 up here in colored, just kind of show you what that looks like. So here's what my number 3 looks like. There's an asymptote, one vertical asymptote, that's the only asymptote. There's not a horizontal one because the numerator is bigger than the denominator. There's not a slant asymptote because the numerator is 3 more than the denominator. So there's no horizontal or slant asymptote. That's what your graph should look like. In your calculator, you need to change the y max. I made mine 25. But originally when you graph it, you're only going to get this bottom piece. And again, that's now you kind of thinking, all right, if there's a bottom piece, there's probably going to be one that's diagonal from it. That's a characteristic that they're going to have. So if you've got a portion on the bottom and you can't see the top part, you got to change the y max. So I made my y max 25. And then you do need to actually calculate the min and the max to graph it. So mine, I just plotted it at the top there because I obviously can't go up to 21. But I just sketched it above. And then when you're doing your increasing interval, from left to right, this piece is increasing, it's going up, and this piece is increasing or going up. You're describing that actually using the horizontal distance. So you describe it actually saying the domain of that piece of the graph. So the domain of this piece of the graph would go from negative infinity to the x value of that max. The domain of this increasing piece goes from the x value of the min to positive infinity. So that's why my values here, they're using the x value of my max and min for the increasing section. So it's that domain.
For the x intercepts, it's the fourth.
Anytime for the x-intercepts, if you set it equal to 0, so you would have negative 1 is x to the 4th. You would take the 4th root of it, but anytime your root is even, you cannot take an even root of a negative number. So because it's an even root, if it's a square root, a 6th root, a 10th root, it's always going to be imaginary.
So the EF is a higher number. Square root.
So you're still taking so you really are taking the 4th root, but because it's negative, you can never have a negative number when you're taking an even root. Because if I have a negative times a negative times a negative times a negative, I would get a positive, but there's no way to get a negative number when you're multiplying 4 things together. Odd is fine. Odd works. You take the square root of any, or the odd root of any negative value. But even root of a negative value you cannot. Other questions? So So then if you look at the last handful of pages, there's a chapter 2 review worksheet in your packet. And that review worksheet starts off with what we kind of were working with the P over Q. So the first two questions ask you to list the possible rational zeros. So that's P over Q. And then it says find the real zeros, because those are the only ones you're going to find in the calculator. So you're going to get the real zeros from the calculator, and then part C says completely factor the polynomial. Write it as a product of linear factors. That means you should have 5 factors if your exponent is 5, because you found 5 zeros. So for number 2 is 3x to the 5th, so there are going to be 5 zeros along with that. 3 of them will be real, 2 of them will be imaginary. Number 3 says write the following. The polynomial is a product of linear factors. It's separate from 1 and 2 because that one's factorable. You don't always have to do P over Q. If you look something up in the calculator and you don't find any x-intercepts, that means the problem can be factorable, because you need x-intercepts in order to use synthetic division. If you don't have any x-intercepts, then you can't use synthetic division. You've got to factor. And then looks like number 4 is an old problem. I think that goes back to section 2, reviewing end behavior, max and mins, graphing it, finding x and y intercepts. So that goes back to section 2. And then 5 and 6 are more of what we were doing with foiling to get a comma. So you've got the rest of the period, which looks like almost 25 minutes. Please ask questions, whatever questions you have. Let me know. If you want to work with somebody, you can.